In this video, thermodynamic cycles will be explained. First, the four thermodynamic processes will be reviewed, including their relations to the first law of thermodynamics. For a deeper explanation of these processes, please watch the previous thermodynamic videos. Secondly, a simple heat engine will be explored, showing the relationships between work, energy, and efficiency for a fixed number of moles of an ideal gas undergoing a cycle of thermodynamic processes. Finally, some important cycles including the Carnot cycle will be explained, as well as refrigeration cycles. There are four thermodynamic processes that can occur to a system of a fixed number of moles of an ideal gas: an isothermal process, an isobaric process, an isochoric process, and an adiabatic process. For a more in-depth explanation of these processes, please watch the first law of thermodynamics and the gas law key concept videos. A thermodynamic cycle can be formed by putting a fixed number of moles of an ideal gas through a sequence of thermodynamic processes until it returns to its original state of pressure, volume, and temperature. Thermodynamic cycles are shown on a pressure-volume graph. Let's explore a theoretical cycle consisting of an isobaric compression, followed by an isochoric process, and finally an isothermal expansion. Consider a container with a fixed number of moles of an ideal gas, a volume V, and a pressure P. On the pressure-volume graph, the system is at point A. Thermal energy negative Q leaves the ideal gas, and under constant pressure, the volume decreases, forming a horizontal line to point B on the pressure-volume graph. Work has been done on the system by the surroundings, giving the work done a negative value. And the internal energy of the gas has decreased, resulting in the ideal gas having a lower temperature. These quantities are related through the first law of thermodynamics. The volume is then held constant as the system undergoes an isochoric process. Thermal energy positive Q enters the system, and the pressure and the temperature of the system increase. On the pressure-volume graph, a vertical line shows the system progressing to point C in the cycle. The internal energy of the ideal gas increases, as does the temperature of the ideal gas. The thermal energy entering the system is equal to the change in internal energy of the ideal gas because no work is done by the system due to the constant volume. The system then completes its cycle through an isothermal expansion. Thermal energy positive Q enters the system, and the volume expands with the ideal gas doing positive work on the surroundings. The system returns to point A, where the cycle can repeat. Because this is an isothermal process, there is no change in internal energy or the temperature of the ideal gas, and the thermal energy Q is equal to the work done, W. If we consider the work done during the cycle, recall that the work done is the area under the pressure-volume graph. Let's consider the thermodynamic cycle discussed previously. Positive work is done when the volume of the ideal gas increases, in this case during the isothermal process. The work done through this process is the area under the pressure-volume graph. Negative work is done when the volume of the gas decreases. For this cycle, that is occurring during the isobaric process. Again, the work done through this process can be found by the area under the pressure-volume graph. Because this is an isobaric process, the formula work is equal to the pressure times the change in volume can also be used. The net work done by the cycle is the sum of the work done by the ideal gas on the surroundings and the work done on the ideal gas by the surroundings. On a pressure-volume graph, this is the area enclosed by the cycle. Note that the area enclosed is the difference between the green and blue shaded areas. Cycles such as this that run clockwise will always have a positive net work and are called heat engines. Heat engines convert heat energy to mechanical work. In a thermodynamic cycle, not all of the thermal energy that enters a system is converted into mechanical work. Some is lost to the system to the surroundings or through friction. The efficiency of the system is the ratio of the work done by the system to that total amount of thermal energy that enters the system. The work done by the system is the area enclosed by the thermodynamic cycle on the pressure-volume graph. The input energy is the thermal energy that enters the system through the different thermodynamic processes. It is assigned a positive value. One important cycle is the Carnot cycle. A Carnot cycle is comprised of two adiabatic processes and two isothermal processes. During the isothermal compression, there is no change in the internal energy of the ideal gas, and the temperature of the ideal gas is the lowest it will be during the cycle. The thermal energy will leave the system, so it will be assigned a negative value. The thermal energy leaving the system will be equal to the work done, and because this process is a compression, this work is also a negative value. The ideal gas will then undergo an adiabatic compression, and no thermal energy will enter or leave the system. The change in internal energy will be equal to the work done, and because the ideal gas is being compressed, this work will also be a negative value. This results in a positive change in the internal energy and an increase in the temperature for the ideal gas. The system will then undergo an isothermal expansion at a constant higher temperature. Thermal energy will enter the system, and because the ideal gas is expanding, the work done will have a positive value. The work done will be equal to the thermal energy entering the system. Finally, the system will return to its original state through an adiabatic expansion. No thermal energy will enter or leave the system, and the change in internal energy of the ideal gas will be negative, resulting in the temperature dropping. Positive work will be done by the gas as a result of this change in internal energy. During the adiabatic processes, there is no thermal energy entering or leaving the system, so the magnitude of the change in internal energy is equal to the work being done. In each of the four processes, work is being done, but thermal energy is only entering or leaving the ideal gas during the isothermal stages. This combination of theoretical processes makes the Carnot cycle the most efficient of the thermodynamic cycles. The efficiency of the Carnot cycle is equal to 1 minus the ratio of the Kelvin temperature of the cold isotherm to the hot isotherm. For example, if a Carnot cycle has a high temperature of 900 Kelvin and a lower temperature of 300 Kelvin, the efficiency of the cycle will be 1 minus 300 divided by 900, or 0.67, 67%. For a Carnot cycle, the larger the change in temperature between the two isotherms, the more efficient the cycle will be. Because all of the processes need to be reversible, these are theoretical processes. If the order of the heat engine processes are reversed, the cycle will work as a refrigeration cycle or a heat pump, where work is done to transfer thermal energy from a cold reservoir to a warmer reservoir. If we consider the two cycles that we have previously discussed, the theoretical three-process cycle and the Carnot cycle, and follow them in reverse order with a focus on the work done on the ideal gas by the surroundings, which is defined as negative work, is much larger than the work done by the gas on the surroundings, or the positive work. This results in the net work done by the cycle being negative. Looking at the first law of thermodynamics for this situation, we know that for a cycle there is no change in the internal energy, so delta U equals 0, and therefore the heat entering the system is equal to the work done. We have determined that the work is done on the system, so the net work is negative, and therefore so is Q, which means that heat leaves the system. Work is being done to pump heat out of the gas and into the surroundings, which is why we call this a heat pump, or a refrigeration process. Heat pumps run in a counterclockwise direction. In summary, a thermodynamic cycle is a closed reversible series of thermodynamic processes shown on a pressure-volume graph. The area under the pressure-volume graph is equal to the work done. Over the course of a cycle, positive work is done when the volume expands and the ideal gas does work on the surroundings. Negative work is done when the volume decreases and work is done by the surroundings on the ideal gas. The net work done by a thermodynamic cycle is equal to the sum of the work done by the gas and the work done on the gas. This work done by the cycle is the area contained within the thermodynamic processes on the pressure-volume graph. There are two types of thermodynamic cycles, a heat engine and a heat pump. For a heat engine, the cycle follows a clockwise path through the processes. The total work done is positive, indicating that energy is flowing from the ideal gas into the surroundings in the form of mechanical work. A heat pump follows the thermodynamic processes through a counterclockwise path. The net work done by the gas is negative, which means that energy flows from the gas to the surroundings in the form of heat, lowering the temperature of the gas. Energy can be lost to the system through thermal energy transfer or through mechanical friction. The efficiency of a cycle is the ratio of the work done by the cycle to the thermal energy entering the cycle. A Carnot cycle, which is made up of two isothermal and two adiabatic processes, is the most efficient cycle. This efficiency can be found through the formula efficiency equals 1 minus the ratio of the temperature of the cold isotherm to that of the hot isotherm. Important to note, these temperatures are in Kelvin. Thanks for watching.